Hello everybody. Folks are posting to the skewness and kurtosis discussion board, and I'm writing answers to some of the initial posts, but I'm not feeling like I can really explain without a video what I want to say to these. So the first thing I want to say is that the skewness and kurtosis analysis that you're doing is very sophisticated. Most researchers actually don't even do it, and it's probably one of the more complex topics that we're dealing with all semester long, even though it comes relatively early in the semester. And also people are taking a really good shot at it, but I think there's a couple things that are confused. All right, and the videos that we gave you didn't provide a couple background points that don't really change the analysis, but maybe help you understand what's going on. All right, so first of all, as a researcher, here's why people would even check this in the first place. If the data are skewed, that means the curve is really peaked or really flat or off to one side or the other, it has skew or kurtosis, then it's not normally distributed. And if it's not normally distributed, that means that you can't use all the inferential statistical tests that we're going to be using later in the semester. So that's kind of why we're raising the point now. So, all the tests that we're going to be using, t-tests, ANOVAs, etc., they're all based on the assumption of normality. So if you think about when we were looking at the normal curve, and we would ask questions like, what percentage of the sample or the population is at one standard deviation or above? And we would say something like 16% are above one standard deviation, right? Or how many are within plus or minus one standard deviation? Well, it's 34% on each side of the mean, and so about 68%. Well, all that assumes that it's normally distributed. If it's not normally distributed, those answers wouldn't be true. And in the same way, if the sample is not normally distributed, or rather if the population is not normally distributed, then the t-tests and the ANOVAs are all built on assumptions that say that it should be, right? So that's why it's important, and that's why we're checking it, and that's why we're doing it now before we get into the inferential statistics. All right, but to be honest with you, in practice, you do not normally see in educational research these kind of analysis being reported. Most educational researchers assume normality and go on their way to doing the statistics they want to do. And also, the data only needs to be roughly normally distributed in order for it to meet the assumptions. Doesn't have to be perfect, just has to be roughly. Now, in the video that we gave you to watch, he had a rule that it had to be that you multiply the standard error by, or you divide the skew and kurtosis values by the standard error, and it should be within plus or minus 2. He said 1.96 to be more precise. And I've seen other recommendation that it be, if you divide it, you get less than 3. Plus or minus 3. But notice he also had to look at the various different plots in the histograms. Why would he ask you to do that if it wasn't a judgment call? You could just look at, is it within plus or minus 2, and you'd be done. But he didn't stop there. He had you look at various things. That's because it's a judgment call. Is it really terribly violating the assumption of normality, and in what way? So that's where looking at the plots can help you. Oh, I see the kurtosis there because I see it's like a big peak right in the middle, and it's not normal at all. All right, so that's the background. Now, the main thing that folks are not doing correctly in their analysis so far is they're not looking at the skewness and kurtosis of the groups. So each group is different, and when you squish them together, then you're really looking at something that doesn't even exist. Semester 1 students and semester 5 students had 2 different experiences, and their data are different, and you squish them together, it's different. Remember in the video that you watched, he analyzed male and female separately. That's because if you put male and female together, I'm not sure what you get, but maybe two different, a bimodal distribution, possibly, because men are generally taller than women. You really have to look at the 2 groups separately. Alright, so I'll quickly show you how we do that in SPSS. It was in the video, but I want to point it out since I think people missed it. Alright, you can't see it, but I'm going to analyze, descriptive statistics, explore. And when you get that, you get this dialog box that you did see in the video. Now I think it makes the most sense to analyze the pretest data. Let's suppose we have a big effect on students. Well, maybe the outcome is not going to be normally distributed, and that was actually our intention. What if we had the success that everybody got up to a perfect score? Let's say this was an achievement test instead of a survey. Got up to a perfect score. Well, the post-analysis would not be normally distributed, but that was kind of what we wanted, so good. But the pre-evaluation probably should be. So I'm going to take what I consider to be the most important variable here, which is TPAC, and that's, I think, the pretest. I don't even know, but it doesn't matter what I'm showing you. See, those labels are important. And here's the important thing. You've got to analyze it by semester. So I'm taking the semester and putting on the factor list. That's our various groups. I'm going to skip the plot thing and just show you what I want to get at with the standard deviation, with the standard error analysis. Alright, so here's the key. Notice there's semester 1, semester 2, semester 3. Each of these groups is different. So if all I'm doing is I'm going to make a mental kind of arithmetic here, and I'm going to multiply this number, or ask myself how much would I have to multiply that to get that. Well, this is already bigger than that, so no problem. If I multiply this by 2, I get 1, which is obviously greater than that. If I multiply this by 2, I get 2, which is greater than that. Plus or minus, doesn't matter. Next one. Yeah, it's kind of close to within 2. This one is pushing the boundaries there. I probably have to multiply by 3 or 4. The standard error set 0.759 by 3 or 4 to get this. A little less than 3 here. Less than 1. Or a little more than 1. A little more than 1. That's fine. That's fine. That's fine, because these numbers, if they're greater than this, obviously if I multiply by 2 or 3, it's going to be greater. So just a very quick inspection tells me that I have only one case where I'm a little bit concerned about the normality, but since I'm really looking for a rough estimate, and rough guidelines are okay, and in almost all the cases it's fine, I think I'm okay with the assumption of normality in this particular analysis that I did. But the important thing is go semester by semester, or group by group. Each group should have different analysis. Alright, so now I'm going to run the analysis that I think you guys, the first few posters have done, which is just the descriptives with the kurtosis and skewness, but not separating it out by groups. And here, standard error of skewness 0.198. I have to multiply that. That one seems okay. It's a little less than 3. But this one here, 0.4, it's starting to violate it. But you see, it's coming out different than I did with the individual semesters. Here I actually may have some concerns about kurtosis, where I really didn't overall when I was looking at the semester group. So it's not okay to smash all the semesters together. You have to look at each group separately. Hope that helps.